Okay, what I'm going to have everybody do here is go into cycle 5, um, and we're going to do what we did before. We're going to cancel out this region, cancel out this region, cancel out this region, cancel out this region, cancel out all this. We're using the simulations right now for all our labs. Cancel out all this. Okay, and then we're going to get here to what's called the ideal gas law equation. Okay, and this is a very, very important equation, and this equation describes the behavior of what we call ideal gases. And an ideal gas is one that's small, and it's one that has really weak intermolecular forces. Okay, we want it to be small so it expands well, right? There's not a lot of gravity pressing down on the particles. And we want there to be weak intermolecular forces so that those particles are not attracted to one another. Remember, gas particles want to expand. That's what they want to do. So now that you studied polarity and you discovered how these partially positive and partially negative charges can create these intermolecular forces, we're now going to minimize those. Okay. Now, gases are really tricky, like I talked about, because gases, you can't see them, right? So we can't grab them and put them on a scale. So because of that, we need to narrow in on 4 things about the gas. We need to narrow in on the gas's pressure. Okay, the pressure of the gas is described as how much force those gas particles exert on the walls of the container. And you saw in the simulation that's measured in atmospheres, and the abbreviation is ATM. Okay, we need to understand the volume of the container that the gas particle is in. And that's the size of the container. You know, gases expand to fill their container. So by understanding the container that they're in, we can get information about those gases with very weak intermolecular forces. And the unit we're going to use here is liters. Okay. Now, be aware, there are times when the volume is going to be given to you in milliliters. So if it's given to you in milliliters, just divide by 1,000 to get to liters. Okay. Conversely, if they ask you for the answer in milliliters, just multiply it by 1,000, and that'll take you right back here to milliliters. But the unit for pressure is atmospheres, and the unit for volume is milliliters. There is N, and N is the amount of the gas measured in moles. Okay. Now, it's very important to remember how to do a mole conversion. So early in the year, I had you guys put a little tab in your notebook where the mole conversion place was, and I need you to go back to that. And that's all about looking at grams mole equals grams mole, where this is the molar mass value. We're going to be solving for that mole value in these conversions. Okay. And the final unit here is the temperature, and that's the kinetic energy of those gas particles. The temperature is going to be measured in this really unique unit called Kelvin, and we use a K to represent that. To get units Kelvin, I'm going to go ahead and erase that here. It's a really simple calculation. Let me explain my logic here. The coldest any gas particle can get is negative 273 degrees Celsius. We call that absolute zero. But if I put a negative value into the equation I'm about to show you, it'll make all these other values negative. So we want a temperature scale that's not negative. So to convert from degrees Celsius to degrees Kelvin, we add 273. Okay. And that would give you what's called absolute zero or 0 Kelvin. So the equation here is your degrees Celsius, you tag on 273, and you have Kelvin. Okay. So there's this cool equation that involves all of these. Okay. And that equation is called the ideal gas law equation. And that equation is written like this. PV equals NRT. Okay, and this is an equation that relates the pressure of a gas, the volume of a gas, the number of moles of a gas, and the temperature. And remember, because gas particles are weird and they expand and we can't see them, we need to understand these three variables. Now, if we were in class, we would have derived these. You're probably wondering, what the heck is this R? This R is a constant, much like pi, and the value for that is 0.0821. And it's got some funky units on it. We're not going to worry about those units right now. So in all of the problems you're about to do, you're going to use this equation just like we use density or mass or volume when we have things that we can see. We're going to use this equation for gases, okay? So every single time we're going to use this equation, I'm going to solve a few for you, and then I'm going to ask you to solve some on your own, okay? And simply all we do is plug in these values, okay? All right, so here we go. So this question says, this example question says, what pressure, okay, that's P, in atmospheres does 22 grams of CO2 exert on the walls of a 2-liter container at 25 degrees Celsius? Okay, so the first thing I do is I list out all my variables and then I solve for it. So there's P, there's V, there's N, there's R, and there is T. So let's go ahead and let's put in everything we know. So pressure is what they're going to be looking for. That's in atmospheres. Okay, that's what they're looking for. Okay, volume is 2 liters because we know that volume is in liters. Right here, this is a very easy equation. Okay. Okay. Now moles. They didn't give me moles here anywhere, but they did give me grams. So I'm going to put that in red to tell you that I'm going to have to do a mole conversion here to make it moles. And we can abbreviate moles, M-O-L. Okay. So sometimes we're going to have to use a conversion. We know that R is always 0.0821. And we know the temperature here was given in degrees Celsius. Now, but remember, it needs to be in degrees Kelvin. So I'm going to go ahead and put that in red as well. And once I have everything in black, then I can go ahead over here and do my calculation. So here we go. So the first thing I need to do is convert this to moles. And I'm going to go ahead and just do that conversion over here on the side. Okay, so what is it? It's CO2. Well, remember, the first thing I need to do is I need to get the molar mass of CO2. We know that 1 mole of carbon is 12 grams, and 1 mole of oxygen is 16, so we're going to multiply that by 2. And we're going to add those up, and we know that 1 mole of carbon dioxide is 44 grams in every mole. Okay, so that's going to go here on the left. 44 grams in every 1 mole. Okay, well, they want to know how many moles are there in 22 grams. So grams is always on the top. 22 grams in every X moles. Okay, so now, you might be someone who can look at that conceptually and say, whoa, if 1 mole is 44 grams, then 22 grams is half a mole, and this is going to be 0.5. Or you're somebody that needs to cross multiply. So if you cross multiply here, you would end up with 44 multiplied by X equals 22, and then X equals 22 divided by 44. Okay, so that's fine. Now we've converted to moles. So they're looking for pressure in atmospheres, volume in liters, okay, and we have that. We have moles. We converted the grams to that. We know R, and now we need degrees Celsius. So remember, Kelvin. So all you do is you take your degrees Celsius, 25 degrees Celsius, and we just tag on 273. It's a really easy conversion. Don't trip about it. And this is going to give us 298 Kelvin. Okay, so here I'm going to go 298. Okay, so great. I have everything, but they're looking for pressure. So now once I have everything in the correct units, I have pressure in atmospheres, I have volume in liters. Sometimes they'll give me milliliters. Now remember, if there's milliliters, I just divide by 1,000. I have my moles, which I converted the grams from. I have R, which is 0.0821, and I have temperature. 25 plus 273 is 298. So I have everything. So now I'm just going to solve for it. So I go PV equals N R T. They want pressure, so I'm going to divide both sides by P. So now V equals N R T divided by P. Now I like to do the conversion first and then plug in. You guys could plug the numbers in first if you like. So now I plug it all in. So moles is 0.5. Okay. R, we know R, that's the ideal gas law constant, 0.0821. You're probably wondering, where does that come from? And I wish I could have the time to derive that from you, but we really needed to do a lab in class for it, but whatever. 298. Okay. And I'm going to divide that by, oh, you know what? We're looking for P here, not V. So you're probably wondering, so this is P, and I would divide these by V. So it's nRT over V. No problem. Same thing. And that's 2 liters. So how am I going to get the answer to this? Well, I'm going to take 0.5 times 0.0821 times 298, press equals. So let me do that in front of you. I'm going to pull up this get calculator. So I'm going to go 0.5 times 0.0821 times 298 equals divided by 2 equals 6.11645. So I'm just going to round that to 6.1. Okay. So 6.1, but 6.1 what? 6.1 atmospheres. ATM. All right. So in summary, I wrote out all the variables of the ideal gas law equation, P, V, N, R, and T. After that, I converted everything to the correct units. And then after that, I wrote out my equation, I manipulated the variables, and I plugged it in. Okay, and I have this atmospheric pressure. Now, by the way, atmospheric pressure at sea level is 1 atmosphere. So this is 6 times that right here. What I want you to do right here is I want you to leave this question right here. Well, actually, let's not leave it. Let's look at it. Would the pressure be more or less if CS2 was used instead of CO2? Okay, H2. So if CS2 was used, that means we would have had a larger molar mass. Okay, and if we had 22 grams of something that was a larger molar mass, that's going to be a lower number of moles. 22 grams of CO2 is 0.5 moles, but 22 grams of some larger molecule, since moles is at the top here, we're going to have a lower pressure, less moles. So lower pressure equals less moles. This is for CS2. Okay, now for H2, 22 grams of H2, well, 1 gram of H2 is 2 grams. So we're going to have a higher pressure because we're going to have a little more moles in that container. Think about that simulation you did. So if you made the actual molecule larger, 22 grams of that molecule isn't really that much, but if you made the molecule smaller, 22 grams is a lot. So something just to think about. So let's do some practice problems here. I'm going to do 2 more, then I'm going to ask you to do 3 in the checkout. Okay, so here we go. The first one. We're going to make our little column here. We're going to write P, V, N, R, T. Okay, I'm just going to put a little dash here to make it easier. All right, 0.01 moles. All right, so where's that? That's right here. 0.01 moles occupies a volume of 0.5 liters. Volume 0.500 liters. At a temperature of 298 K. 298 K. And we know this, 0.0821. Now, what is the pressure in atmospheres? So question mark, atmospheres. Now notice here, because the pressure is asked for in atmospheres, because the volume is in liters, because this is in moles and that is in Kelvin, we don't need to do any conversions. So I didn't put anything in red. In that previous problem, moles was given in grams, and I needed to do that conversion. So what am I going to do? I'm going to write out my ideal gas law equation. I'm solving for P, so I'm going to divide both sides by P. I'm solving for, I made the same mistake again. Jeez. So P equals nRT over V, 0.01 multiplied by 0.0821 multiplied by 298 divided by 0.5. Okay, so I'm going to pull up my calculator. And I'm going to go 0.01 times 0.0821 times 298 equals that divided by 0.5 equals 0.48. 0.48 what? Okay, 0.48 atmospheres. Boom. Okay, let's try this second one here. All right, these are all gas problems. Anytime you see gas, the equation we're going to be dealing with is PV equals nRT. Okay, so P, V, N, R, T. You know, I don't even read the problem. I just go through and grab the variables. So 10 grams of neon gas. Grams, grams, grams. I don't see grams anywhere here. Well, that relates to moles, though. So I'm going to need to do a conversion there. Pressure, 4.5 atmospheres. Okay, that's in the correct unit. So 4.5 atmospheres. That's good there. Volume, that's what we're looking for in liters. We know R is 0.0821. And temperature, 50 degrees Celsius. Well, temperature is supposed to be measured in Kelvin, okay? But we're going to go ahead and put it here in 50 degrees Celsius, but I'm going to put it in red. Now, you can do this however you want. If you don't have different colors, just put a star next to it. All right, so let's do our conversions real quick. I'm going to do the conversions over here. Okay, so I have 10 grams of what, though? 10 grams of neon. 10 grams of neon. So if I go to the periodic table of elements, periodic table of elements, and I wait, and I wait. What, dude? What, bruh? Come on, bruh. Let's go. Mr. Neon, I know what it is. I'm not going to open that, dude. Why do you keep asking me that? What? I just said yes. So slow. I mean, I know what the molar mass is. I'm just being silly. Okay. The reason I'm bringing this up is neon's molar mass is 20. Its atomic number is 10. Okay, so don't be fooled by that. Okay, so I go to neon. Neon's molar mass is 20 grams in every 1 mole. But they want to know how many moles are there in 10 grams. Okay, so you can look at this like we did last time and just say, listen, dude, if I have 10 grams, but there's 20 grams in every 1 mole, that's half. Okay, or you can do your cross multiplication and say 20x equals 10. X equals 10 divided by 20, which is 0.5. Okay? Sorry. That was out. Okay, and now, what do we do to get from Celsius to Kelvin? We add 273 right there. So I take this, I go plus 273. Okay, so 273 plus 50, 323 Kelvin. And I want to write that in black because my conversion has already happened. 323 Kelvin. Okay, so now we're solving for volume. Okay, so we got to get P volume by itself. So V equals nRT over P. N is 0.5. R is 0.0821. T is 323. And P, in this case, is 4.5 atmospheres. Okay, so then I'm going to bring over my legit ghetto superstar calculator. 0.5 times 0.0821 times 323 equals divided by 4.5 equals. So 2.9464. So for you, just round so the number looks okay. I mean, rounding is a whole other issue in chemistry, which we're not going to get to right now. So I'm going to call this 2.9. I could call it 2.95 if I wanted to. I'm not going to worry about rounding. But the unit is important. 2.9 what? 2.9 liters. Okay, so we did 2 example problems, and now here we have 3, 4, 5 here for you to do. And that's what I'm going to have you do in the checkout. Okay? Take care.